back. So we start today's session. And for the last lecture on the series, Volodymyr Nekrashevych will talk us about etale groupoids.
Yes, thank you. So let me remind you the theorem that I formulated last time, and I will illustrate it by examples then. So theorem, let A be the homeomorphisms of a Cantor set X such that A square and B square are identities and the action of the corresponding dihedral group is minimal, minimally acting on X. And then let, so suppose that A has a fixed point psi, and let A and B be fragmentations of A and B, and suppose that no germ of any element, no germ of an element. Sorry, the germ of every element of A at psi is different from the germ of A. Then this group, the group generated by A and B is infinite and torsion. So I mentioned that any minimal action of the infinite dihedral group, which is not free, so which has a fixed point, you may always assume that it's the generator that has a fixed point, can be fragmented so that the fragmentation will satisfy this condition. Let me repeat it because I was very quick at that time. So here is a space X, you take point psi, find a sequence of Clopen sets, a descending sequence of Clopen sets, such that the intersection is the point psi. So take some metric and stake Clopen balls, and then replace UI by A of UI intersected with UI. Then you will get, again, a descending sequence of Clopen A invariant sets now. These intersections will be invariant under A. So then, after replacing, we may assume that UI are A invariant. Then throw away any repetitions so that you get a strictly decreasing sequence. And then take pairwise differences of the neighbors. So you will take, let's say, W1 is U2 minus U1, W2 is U3 minus U2, and so on. So you partition the whole space X with psi removed into these Clopen sets. So you have WI is a Clopen partition, infinite Clopen partition of X minus psi. And now you can split the whole space into 3 pieces. You just take any partition of natural numbers into 3 disjoint sets. So you take, say, n1, n2, n1, n2, n3 is a disjoint partition. A partition of n into 3 invariant, into infinite sets, and then take P1 to be the union of all these Wi's where I is in N1. Pi2 is the union of Wi's where I is in N2. And P3 is the union for I in N3 of Wi. So these open sets will accumulate on Xi. And then, for example, well, not for example, in this case, you partition A the way I showed last time. So you act AA and identity on, you act by A on 2 petals, and A act by identity on the 3rd petal. Of course, you can make more pieces and partition into more elements. So there's a lot of freedom. And you see that there is a lot of freedom here. You can really choose any partition, then choose any subsets. So, and actually, if your action, if you pass to the full group, you know the theorem that I formulated that different actions will produce different groups. Of course, you have to prove that you get different actions, but mostly you will get different actions. So you really get uncomfortably many different groups, even from one single minimal action of D infinity. And of course, there are many different minimal actions of D infinity itself. So really, you get very many groups. So these are examples of finitely generated infinite torsion groups. And for a while, that was a big open question. It was, if such groups exist. It was solved by Golden Shafarevich in late 60s. Then there is a strong, harder question whether you can find such a group where the order of elements are bounded. Actually, here they are unbounded. So there's not an answer on that harder question, which was solved later by Adyan and Novikov, also in, I guess, late 60s, but after Golden Shafarevich. And by now, there are 3 classes of infinite torsion groups, infinitely generated torsion groups, the Golod-Shafarevich examples, so-called Golod-Shafarevich groups, and then all kinds of examples constructed using methods developed for solving the harder Burnside problem with bounded exponent. And in these 2 classes, the method is roughly more or less follows. Take free group and then throw in relations. And each time you add a very, very long relation. And next time you add even much longer relation. In such a way that you are sure that at the end you get an infinite group. And then you add more and more relations to make this group torsion. The way you ensure that the group is infinite is either using some kind of geometric small constellation theory, or maybe a combinatorial small constellation theory. That's what's done in Adyan, Olshansky, Gromov, Rips, and all their work, or using Shafarevich inequality to prove that the group is infinite. But in all these cases, at least in all known examples, the groups that you get are big, precisely because you take very long relations so that you will be sure that you don't make this group small. So you ensure that it is not small by, you ensure that it is not finite by ensuring that it's very big. And in this sense, these groups are really big, so they are non-amenable. At least in the all-known case, for Goloshev groups, it's a theorem that it's non-amenable. And then there's a third class, which until recently consisted of isolated examples. The Grigor-Chuk group, Gupta-Sidki group, and some other groups. They were acting on rooted trees. Now this is some form of development of those examples. So let me explain you why Grigor-Chuk group is a particular example of this theorem, so how it is a particular example. So remember that there is an action of the infinity on the binary alpha, on the Cantor set of one-sided binary sequences coming from the adding machine or from the odometer. You can consider infinite sequences as dyadic integers, and you have operations of adding 1 and operation of changing sign. So A and B act, say, x goes to minus x, and B acts, x goes to 1 minus x. Or maybe other way around, actually. It's better for me. So there is a nice way of representing them, which is different from that encoding which I mentioned. It's different from the encoding coming from binary enumeration system. It corresponds to something called gray code. So there's another encoding of integers called gray code, which has the property that if you move from n to n plus 1, you have to change exactly 1 bit. You don't have to change many bits as in the usual encoding. And with that encoding, the action is as follows. A acts as on the binary tree as switching these two subtrees, or symbolically, it changed 0 to 1 in every initial 0 to 1 and 1 to 0 in every word. And B acts like this. So it acts like A on every subtree, kind of hanging from this infinite branch. So symbolically, it means that assuming that this is 0, if you act on 0 W, it stays 0, but then on the rest, you act as A, as here. And if it is 1, then you just repeat everything. So it's 1 BW. So it's not hard to check that this is, this will give you a minimal action on the space of all infinite sequences. And it's the same action as here, but for a different encoding of integers. That's the so-called gray code encoding. OK, so A doesn't have a fixed point. Actually, now I think that I should have done it the other way around. But traditionally, this is the word. So B has a fixed point. We can fragment B using this technique. So what will be these sets U1, U2, U3? A natural choice for such sets will be just subtrees, boundaries of the subtrees growing from the rightmost branch. So U1 is the whole Cantor set, so the whole boundary, that's U1. Then everything growing from here is U2. Everything growing from here is U3. This is U4, and so on. So W's are these boundaries. So boundary of this subtree is W1. Boundary of this subtree is W2. This is W3. This is W4, and so on. So now you do this trick. You choose which natural numbers belong to N1, which belong to N2, which belong to N3, and you will get precisely, exactly the Grigor-Chuk groups. So the first Grigor-Chuk group is the kind of natural choice that you choose. N1, N2, and N3 are just natural numbers corresponding to residue mod 3. So you take 1, 4, 5, and so on as one set. No, sorry, 1, 4, 7, 10 as one, and then 2, 5, 8 as the other, and 3, 6, 9, and so on is the third set. So that's the first Vygotsky group. But actually in his paper on growth of groups, he considers all of them, and they are exactly what you get using that construction. But this action is actually continuous, so if you want to construct finitely generated simple groups, it won't work, because you can get a simple group taking the full group of this, but it won't be finitely generated. And if you take not a finitely generated group, it will be residually finite. So it's never simple. So you need a minimal expansive action to get, for example, if you're interested in simple groups, to get simple. So what could one do? One could take a rational rotation, for example, but kind of dihedral version of it. You take the circle, take two diameters, and consider reflections with respect to these two diameters. So A is a reflection with respect to one diameter. B is the reflection with respect to the other diameter. And then if the angle between these diameters is irrational, then this will give you a minimal action on the circle. You can transform it into an action on a Cantor set using the standard trick coming from, for example, something called Donjoy examples. For instance, you can take one end of this diameter and split it into two points. So instead of so if you parameterize this by real numbers, instead of number alpha, you will get number alpha minus 0 and alpha plus 0. And then propagate this by the dynamics. So you split in the same way all points in the orbit of this angle alpha. And take the intervals as your basis of topology. So open intervals, but say open interval from A minus alpha, sorry, A minus 0, alpha minus 0 to beta plus 0 is actually a closed interval from alpha plus 0 to beta minus 0. So just take open intervals, and that will generate topology. And since the orbit is dense, that will be a Cantor set. Now, if you split this in two and split the orbit of this point won't be in the orbit of this point. So this point won't be split, and A will have a fixed point here. And then you can do this trick, and you will get an action of you will get a fragmentation. You will get a torsion group. Now, little fact is that if the action of the infinity is expansive, then the action of the fragmentation is also expansive. That's a little lemma, which is not hard to show. Basically, the idea is that for any pair of points, xi1 and xi2, and say for A, there exists an element of the fragmentation such that G of xi1 is A of xi1, and G of xi2 is A of xi2. So this, for one point, that was an axiom in the definition of fragmentation, but it is true for pairs of points because of the condition of, because of the conditions of theorem. So I will not show this, but that's easy to show. And therefore, if the action of the dihedral group is expansive, then the action of the fragmentation is expansive because for any points, there will be an element of the dihedral group which will move these 2 points far apart. And then using this lemma, you will find an element of this fragmented group which will do the same. So you don't have to think much about expansivity of the fragmentation. It will be automatic as soon as the action of the dihedral group is expansive. So the action of the dihedral group here is expansive. So for any fragmentation, whatever fragmentation you take, you get an expansive action. So this will be expansive. Take the full group, or take rather the alternating group of the action of the groupoid of germs. So this will be finitely generated by the theorem which I formulated before. And it will be a particular case of that theorem again. So it will again come from fragmentation of A and B. Maybe fragmentation to more pieces. But it will be again a fragmentation. So this will be again, rather it will be a subgroup of some other fragmentation. So we know that this is torsion. So this is also torsion. We know that it's finitely generated. And we know that it is simple. So this way you construct simple, we get simple finitely generated infinite torsion groups. So such groups exist before, so-called Tarski monsters, but probably it's better to call them Olshansky monsters. Yeah. Yes, the point is that it's because the original action of the circle is not expansive, no. But we cut this circle into a Cantor set, and that makes it expansive because whatever 2 points on the circle you take, say x and y, you can rotate them around so that the images will contain this point. And this is where you have cut it open. So you created some distance which is bigger than 0, like a lower bound. So you cut, you have, say, there is also some cut here. So these two points will belong to 2 Clopen sets, which you fix in advance. So you take in advance 2 Clopen sets, and for any pair of points, you can move them so that these 2 points will belong to different Clopen sets. And then there is some delta distance between these 2 Clopen sets. So this way, so that's a way of making it expansive. Okay, and this wasn't very explicit, right? I just said that you can do it. You can do this construction, then do this construction, and you get a finitely generated simple group. So I guess it's better to have an explicit example. So here is one coming from the golden mean rotation. So if you take this, if you use this construction and with the angle equal to the golden mean, and take some, actually the most natural choice of WIs, which comes from the approximants. You rotate the point and take the moments when it comes closest, first moments when it comes closest to this fixed point, use it as cutting places for these UIs. Anyway, the result is as follows. You act on the boundary of the set of sequences in the alphabet 1, 2. So you take the infinite sequences with the alphabet 1 and 2, and take the following transformations. So A0 transforms 1, 1W to 2W, and 2W to 1, 1W. Something is missing here. What's missing? I mean, what sequences are missing here, what were not covered? 1, 2. So with 1, 2, we just don't move them. Then B0 acts on 1, 1W as 2W. It acts on 2W as 1, 1W. Acts on 1, 2W as 1, 2. And then C0 of W. C0 of 1, 1W is 2W. C0 of 2W is 1,1W. C0 of 1,2W is 1,2. D0 of W, and D0 of 1,1W is, now we have to do something interesting, say 1,1W. D0 of 2W is 2W, and D0 of 1,2W is 1,2B0W. So we are done with definition. So this gives you a recursive definition how to act on infinite sequences. So B0, C0, D0, they are fragmentations of one of reflections with respect to diameter. And this is another thing. Now this generates a finite group. It's not interesting. So we need more. So you define A1 as, well, when X is any letter, A, B, C, or D, you define X1 by the rule that X1, if it acts of 1W, it acts by X0 on the tail. And then it ignores anything starting with 2. And X2 does the same, but other way around. If it is 1, it doesn't move it. If it is 2, it acts by X0. So we get how many? 12 generators here. Some are redundant. Actually, B0 is equal to B0 times C0. Sorry? Yes, thank you. Yeah. So this is what you get from particular choices in this example when the angle is the golden mean rotation. So this group it's a group. It's a f of g for some groupoid for some g. So for some groupoid of germs, it's the full group, the full topological group. And its derived subgroup is A of G. So if you take the derived subgroup is simple of index. If you think a little, it's not hard to see that it's 512. No, but it's really not hard to see. It's 2 to the 9. At least to guess. Maybe to prove is difficult, but to guess that it must be 512 is not hard. So in particular, it is finitely generated. If you have a finitely generated group and you have a subgroup finite index, it's also finitely generated. So this will be a simple torsion, infinite simple torsion group. Sorry? It's A naught, B naught, C naught, D naught. Any of them. So that's a kind of general rule how you get A1, B1, A2, B2, and so on. So as I mentioned, simple finitely generated torsion groups were known before, constructed by Tarsky monsters. So these are groups where for some prime p, every element has order p, but they're infinite, they're finitely generated. But they are definitely non-amenable. So they are really big, really monsters. This is a much more tame thing. So it's really, they are amenable, and in a little bit later, I'll formulate a theorem which implies that this group actually has intermediate growth. This has sub-exponential growth, so it's really small. It's something very different from Tarsky monsters. And it's very easy to work with it. I mean, the word problem is solvable in polynomial time in these groups. They're really tame. Now, well, I'll talk about amenability a little bit later. Now, let me give you one more example, which was suggested to me by Yves Cornelier, that you could do these fragmentations in a much nicer way for some examples. And that gives you another unexpected torsion groups, which so take a torus, R square mod z square, and take 2 points in this torus, v1 and v2, and consider transformation x goes to negative x plus 2v1, and x goes to negative x plus 2v2. So 180 degrees rotations around v1 and v2. So if v1 and v2 are sufficiently random, then this will also a minimal action on the torus. Right, so if they are independent over Q, and, well, there is famous Kronecker theorem, which ensures that this will be, so if V1, V2 is a generic pair, then this defines a minimal action of the infinity. So let's take, for example, represent torus as a square, and take one rotation to be rotation around the center of the square, and another rotation is a rotation around some other point. So in terms of the square, it means that you split it into 4 rectangles and rotate each of these rectangles 180 degrees. But this point must be sufficiently random. So it must be have both coordinates. If you take 2 coordinates and 1, these 3 numbers must be independent over Q. If they're independent over Q, this will generate a minimal action of the infinity. But now you can fragment this like this, for example. You split this square into, say, 3 sets. This is set number 1. This is set number 2, and this is set number 3. So you get 4 rearrangements of the square. So you cut square into polygons and rearrange them. You have 4 such transformations, and they will generate a torsion group. Namely, you have this is A, and then B will be say acts identically here and rotates this shape around this center by 180 degrees. The other one, it does this. It rotates these 2 around the center of the square by 180 degrees. And the other one is this. Take this part and rotate it around the square 180 degrees. Yep.
Can you repeat?
Top right. You take this rectangle and rotate it 180 degrees. Yeah, central symmetry around this point, around this point, around this. Any rotation of the torus has 4 points around which it is rotated. If you take rotation by 180 degrees, it will have 4 fixed points. Like here too, this rotation has 4 fixed points. This is 1, this is second, this is third, and this is fourth. So every rotation has 4 fixed points. So here you see them explicitly, but on this picture you cut them so you don't see them, but they are there. Okay, so this is an example of the infinite torsion group. I don't think that, I'm sure that no such simple, easy to formulate examples. I don't think that, this is the first example of a infinite jointly generated torsion group of local piecewise isometries of a polygon. And of course, here you have a lot of freedom too. These lines by which I cut don't have to be straight. You can take some curves, which are central symmetric. You can take hexagon instead of square, and so on. Yep.
To
Yeah, formally, if you want to apply the theorem directly, you have to blow up it into Cantor set, but don't blow up this point. This must be a fixed point. Yes, so that's how you apply the theorem. But you can define this group without talking about Cantor set. Just the group of, say, ignore sets of measure 0, for example, and look at this as a... Okay, I don't have much time, so no proofs today. Now I want to talk about growth. And then I'll talk about amenability, and then maybe I'll tell about some ideas of the proof. Actually, the proof of torsion is very easy. It's not, I could explain it in maybe 15 minutes, but I don't have them, perhaps. No. So now, anyway, the main tool of proving the theorem is to study graphs, orbital graphs. You study orbits of the action. So take an orbit. Say of this A and B group, and connect a point X through point Y, and label it by a generator if S of X is Y. So we get a labeled graph, oriented graph labeled by generators. But in fact, these generators are involutions, so I won't orient it, because if Y is X, if S of X is Y, then Y is S of X, because all generators are involutions in this case. So you will just get a graph, maybe with loops and multiple edges, definitely with multiple edges, and actually end with loops in this example, which such that edges and loops are labeled by the generators. Now, the action of elements of A act either as the generator A of the dihedral group or identically. B acts also as B or identically. So this graph will be basically the same as the graph of the dihedral group, except for edges labeled by A in the action of the dihedral group will be replaced by some multiple edges, some collection of multiple edges which correspond to the generators that move this point here, and loops which correspond to the generators that fix these points. So in the dihedral group, if you take the orbital graph for the dihedral group, you will get some edge A. In this group, this edge A will be replaced by something with some labelings. And same here, if you had B, it will be replaced by something. So some elements of B will act as B, some will act identically. So some will be edges, some will be loops. But that's all what will happen. And orbits of the dihedral group, the orbital graphs of the dihedral group look like this. There is no choice. You have A, B, A, B, A, B, and so on. So that's how the orbital graphs of the dihedral group look like. Well, of course, so it may go infinite to both sides, or at one point you may have a loop, and then it goes infinite. The orbits must be infinite because we assume that the action is minimal, so we cannot have finite orbits. So there are only 3 kinds of orbital graphs for the dihedral group. And then for this fragmented group, this graph will be by replacing A's by something like this and B's by something like this. But at different places, you replace A by different pictures because some generators act trivially on some points and as A on the other points. So at some places, that generator will be a loop. At some other places, that generator will be an edge, a non-loop edge. So it means that you can look at these orbital graphs as at some kind of bi-infinite sequences or one-infinite sequences over some finite alphabet. So there is only finite number of possibilities for this replacement actually equal to the number of pieces that you get in that fragmentation. And there is some finite alphabet here, some finite number of possibilities. So you replace each such pattern by such graph by some other graphs like this, and at every place there is finite. At each place there is finitely many possibilities, so you get actually a subshift over finite alphabet. So so we say that, definition. We say that the orbital graph is linearly repetitive if every finite, in this case, finite connected subgraph, but in this case, these subgraphs, I will call these subgraphs segments, so they kind of correspond to finite subwords. So every finite segment of length L appears infinitely often in this graph as an isomorphic copy with gaps of length not more than CL for some fixed L, for some fixed C. I guess it was already mentioned here that if you have a minimal shift, for a shift to be minimal, the criterion is that every finite subword appears in every infinite word everywhere with bounded gap. So if you take any, minimality, if you take any segment sigma, isomorphic copies of this segment sigma will appear everywhere, so that the gaps between neighboring appearances is uniformly bounded by some number depending on sigma. That's a criterion for a subshift to be minimal. So in our situation, since the action of A, B is minimal, these orbital graphs will be repetitive in this sense, that if you take any segment, you will see its isomorphic copies everywhere with bounded gaps. But in general, for a minimal action, this gap, the length of this gap might be very big. So there is some upper bound, because there is only finitely many possible segments of length of a given length L, but this upper bound may be arbitrarily big. So, but if the smallest possible, the best case is when this gap is of linear size, so bounded linearly on the length of sigma. So, for example, you can formulate the same for shifts. So not only for orbital graphs like there, but for shifts, maybe it's even more appropriate. There's a theorem by Dominique Lenz. It's not very complicated, actually, that minimal substitutional shifts are linearly repetitive. So, in fact, for substitutional shifts, if minimality and linear repetitivity are equivalent. So, if it is linear repetitive, that's, well, it's obvious. If it is linear repetitive, then it is minimal for subshift. But yes, this is the statement. The fact that that's the same is obvious. It's not, as you know if you know the statement. So the theorem which I want to formulate now is that if the orbital graphs, so let A and B, let A, B be fragmentations. So they satisfy the theorem, let's call it 1. So that theorem. If the orbital graphs of this group are linearly repetitive, then this group has intermediate growth. So it means that, so what is growth of the group? It's for number R is the number of group elements which can be written as a product of R generators, at most R generators. So intermediate means that it is slower than any exponential and faster than any polynomial. So for a long time, it wasn't known if such groups exist at all. In the 80s, Grigorchuk constructed his groups and proved that they have intermediate growth. But now we have and for a long time, basically, that was the only example. So you could build upon that example and produce very many different groups with many different growth types, especially very nice results in this direction were obtained by Bartoldi and Anna Erschler, but also Kasabov and Pak. But all these constructions were based on the Grigorchuk group. So there basically were no other, and some very similar examples. There were no other examples. In particular, it was open if groups of intermediate growth can be simple. So Grigorchuk group is residually finite, and it's not simple. And all other constructions, they had Grigorchuk group somewhere there. So usually those groups had Grigorchuk group as a quotient, for example. So you couldn't construct simple functionally generated groups of intermediate. You couldn't construct simple groups of intermediate growth before, basically because there was only one example of such a group. This gives you a machine to construct them. For instance, here this group has intermediate growth because I said that it is constructed from golden mean rotation, but maybe you know that golden mean rotation is also a substitutional dynamical system. Can be realized as a substitutional dynamical system. So if you look at that from that point of view, you can show that this is linearly repetitive, and therefore it has intermediate growth. Yes, Grigorchuk examples are covered by this theorem. Okay, I'm out of time, so let me give you one more theorem related to amenability, and that will be it. So all these groups, all groups which are covered by the theorem that I'm currently erasing right now, they are all amenable. And one of the ways of showing that they are amenable is to use theorem of Yushchenko-Monod. Another way is to apply a generalization of that theorem, which is due to Yushchenko, de la Salle, and me. So, and I want to formulate it for a couple of reasons. So, Yushchenko, de la Salle, and me. Let G be a groupoid of germs such that the full group of this groupoid is amenable. Let G be a finitely generated group of homomorphisms of the unit space such that the following conditions are satisfied. First, for every group element, the number of points X in the unit space such that the germ does not belong to the groupoid G is finite. It acts, its germs belong to the groupoid G, except maybe for a finite number of points. Two, the orbital graphs of G are recurrent in the sense of random walks. So if you take a simple random walk, then it visits the origin infinitely many times. And third, the groups of germs. So you take all germs fixing a given point. So you denote it G with X are amenable. For example, if they are trivial, that's satisfied, then G is amenable. So all these groups satisfy these examples for some AF groupoids. So if groupoid G is AF, then the full group is locally finite. So it just comes from permuting finite paths in the corresponding Bratteley diagram. So for example, if you have a minimal action, I would say moreover, the space of unit is compact. Yeah, we assume that it's Hausdorff, but not the. Then the full group of the action is also amenable, because these conditions will be satisfied also for full group. So if you take a minimal homeomorphism of the Cantor set, and then from the other mini course, you know that it satisfies these axioms, because there is the AF groupoid, which is changing one beginning of a path to another. And that minimal homeomorphism acts like that AF groupoid, except for 2 points, except for the minimal path in the Bratteley diagram and the maximal path. So only at these 2 points the germs are different from the AF groupoid. The full group of the AF groupoid is locally finite, so it's amenable. And then the graphs are just lines, just Z, so they are recurrent. And the groups of germs are trivial, so they are amenable. So this way you see that this theorem implies that the full groups of minimal Cantor dynamical systems are amenable. Essentially, that's also the original proof of Yushchenko-Monod. They use locally finite groups there, even though they don't use Bratteley diagrams. But it is implicitly there. But there are many more examples. In fact, what I wanted to mention, like my final remark, I mentioned that there are two big classes, like classical big classes of torsion groups, Golod-Scheferage groups and groups obtained using small constellation theory. And then currently there is only one more class of groups. So all the other groups, torsion groups which are not based on those two, are in this class, and all those groups are obtained from some AF groupoids using this construction. So I would say the corresponding groupoids are AF bidiscrete. So you have some groupoid. Inside that groupoid, you have an open AF subgroupoid. And the set theoretical difference is a discrete set. So all these other torsion examples are in this class. But I don't know yet. It would be an interesting project to understand how among all groups, which are almost AF in that sense, so that AF except for finite number of points, how to single out the torsion groups from there. So my theorem gives it for D infinity, but that's for the dihedral group, but that's a particular class. There are examples like a Gupta-Sitke group, which is not there. So it would be interesting. Okay, unfortunately, I don't have time to give even an idea of the proofs, but that's it.